Lesson 8.3, Estimating a Proportion. In the first two sections of this chapter, we learned about confidence intervals and how they're used to estimate a population parameter. We're often interested in estimating the proportion, P, of some outcome in an entire population. Some examples: what proportion of US adults are unemployed right now? What proportion of high school students have cheated on a test? Or what proportion of pine trees in a national park are infested with beetles? Now that we understand what a confidence interval is, we're going to talk about how we create a confidence interval for a proportion. The first step we take before we create the actual interval is to check the conditions. So the first condition is that we have data that comes from a random sample from the population of interest. This includes checking the 10% condition which we checked with sampling distributions, and the fact that our sample is less than 10% of the population. Then we're going to go ahead and check the success-fail condition, which we also checked with sampling distributions, where both NP and NQ, the book will denote Q as 1 minus P hat, are at least 10. And just a reminder for something we learned way back in chapter 4, when we were talking about sampling from a population, that sampling had to be collected at random. If it wasn't, we can't generalize those results to a larger population, which is why margin of error in a confidence interval doesn't account for any kind of bias introduced in the way that we're collecting our sample. So let's take a look at this example. Dr. Godlewski's class took a sample of beads with the goal of determining the proportion that are red. They got 107 red beads and 144 other beads. Their point estimate for the proportion of red beads in the container. Point estimate is the result of the sample, so it's a p hat, and it's 107 out of 251. That 251 comes from adding these two numbers together because that's the total number of beads, and we get our point estimate of 42.6%. First thing it's asking is for us to check those conditions. The class selected a random sample of the beads. We're going to assume that 251 is less than 10% of all beads in the container. And when we check that success-fail condition, we see that we get 107 successes and 144 failures. This 42.6% is a rounded version of 107 out of 251. And just note that our n times p is always the number of successes, and our n times q is just those number of failures. Both of those conditions are met, which means we can go ahead and create a confidence interval for the true proportion of red beads in this container. But what would happen if one of those conditions were violated? Well, in that case, it's possible that there's some kind of bias that's present in our data collection process. And since the margin of error doesn't account for bias, there's no reason to create a confidence interval. So in other words, if we have a violation of one of those conditions, we're going to stop the process and not create that confidence interval. In the last section, we talked about the structure of confidence interval and how we started with a point estimate, which would be a p hat. It's the result of our sample. And then we're going to add and subtract some margin of error, which is accounting for the natural sampling variability. So we have our point estimate right in the middle of our interval. It's the exact midpoint. And then we move out above by adding and below subtracting that margin of error. So p hat is right in the middle, and the distance from the middle to the boundaries of our interval will be that margin of error. Determining what that margin of error is slightly more complicated than finding the point estimate because there are two components used to calculate it. We have the confidence level of C%, typically 95%, and we have sigma p hat, which is the standard deviation of the sampling distribution of a sample proportion. Last chapter, we talked about these sampling distributions for sample proportions, including the standard deviation, radical PQ over N. Now, the problem is we don't know what P is. Okay? In the last chapter, it told us what P is, the true population parameter. But now we're just going to have a P hat. Okay? We're using that P hat to try to figure out what is P. Okay? And we estimate it with a confidence interval. So we're going to change our equation slightly by just putting hats on those equations. We're going to use the results of our sample to estimate that standard deviation. And we can do that as long as we're meeting that large counts, that success-fail condition, where we have at least 10 successes and 10 failures. We're also going to tie in the empirical rule, which we learned way back in chapter 1, 68, 95, 99.7 rule. If we move out 2 standard deviations from the mean, we're going to include about 95% of the data in a normal curve. And we're just using it in reverse. When we have a value, if we move out 2 standard deviations, P is going to be within 2 standard deviations of the mean about 95% of the time. Now that 2 in the empirical rule is actually just an estimate, and we're not always going to go out 95% for 2 standard deviations. That can change, and it's going to change with what's called a critical value. That will depend on the confidence level. So the critical value is a multiplier that makes the interval wide enough to have that capture rate. So if we said 68% confidence level, we'd go out about 1 standard deviation. Again, that's an estimate. If we had said we have 95% confidence, we'd go out about 2 standard deviations. That's an estimate. It's actually about 1.96. And if we say we are 99.7% confident, we would go out about 3 standard deviations. Like I just said, the 68, 95, 99.7 rule are estimates. They're used for quick calculations. We're going to be a little more precise now that we're further into the course. So we're going to find the critical value, denoted by Z star, for a 95% confidence interval. So to start, confidence intervals are always moving out from the center of the curve. So that 95% is cut out of the middle, because we're going to start with our point estimate, and we're going to put that right in the middle, and we move above it and below it the same amount, which is going to be our margin of error. So since there's 95% in this range here, that leaves 5% left over, because our curve is going to total 100%. So between this left tail and this right tail, we know it's going to be the other 5%. And since a normal curve is symmetric, that 5% is going to split exactly in half, 2.5% on the left, 2.5% on the right. Now, this becomes a problem just like we did earlier in the year when it's giving us some kind of percentage, right? We're given a percentage and we want to find the z-score for that value. So we're going to look this up in the middle of the table, and then we're going to move to the outsides to see what's the z-score that would leave that area, that percent area in that tail. So we go to our yellow table, we look for the closest thing we can find to 0.025, and in this case we're going to find it exactly at negative 1.96. So our z-score is going to be plus minus 1.96. Plus minus because it's a margin of error and it moves to the right and to the left because of that plus minus sign. When it comes to terminology, standard error and margin of error sound like the same thing, but they're not. Standard error estimates how much p hat varies from p on average, while the margin of error estimates how much we expect p hat to vary from p at most. And that's an important distinction because when we create our confidence interval, we're creating a range of values, and we're hoping that the true population parameter is within those values. So in other words, how far at most do we expect that population parameter to be from our p-hat? When we're talking about the standard error, we're talking about the standard deviation of the sampling distribution and the fact that when we take a sample and take another sample, those two values won't be the same. We'll get different results every sample we take, and they're going to differ from each other by that standard error on average. When we calculate the margin of error, it's a combination of that critical z-score that we talked about earlier and the standard error. So the equation for a confidence interval is given here. We see that the point estimate p-hat is what the interval is built around, and then we're adding and subtracting the margin of error. So the margin of error is that critical z-score times the standard error of that sampling distribution. Again, they use 1 minus p instead of q, and we'll write it as radical p hat q hat over n. And that z-score, like we discussed, is the critical value for that specific level of confidence. So to finish up, let's calculate a confidence interval start to finish. Dr. Godlewski's class selected a simple random sample from her container of beads and got 107 red beads and 144 other. We're going to make a 90% confidence interval for P, which is the true proportion of all beads in the container that are red. So to start, we'll find our point estimate, which is the p-hat. 107 out of 251, which is just the total number of beads in our sample. We get a p-hat of 42.6%. Next, we're going to use this confidence level to determine what's that critical z-score. So that 90% gets cut out of the middle of the curve. And since there's 90% in the middle, that leaves 10% left over. That 10% gets split up to 5% in each tail. This is a percentage, which means we're going to look for it in the middle of our yellow z-score table, and we're going to find the closest thing that we can. In this case, it's exactly in between negative 1.64 and negative 1.65. And when it's exactly in between two values, we average them. So in this case, we have negative 1.645. Now, just a note, we could also do it with this other side, the right tail, which is 5%. But remember, we're always looking for the area to the left of it. So if we looked up 0.95, we'd get that same value, just positive. Plug everything in. So we have our p-hat plus minus that z-score times the standard error, p-hat q-hat over n. The margin of error ends up being 0.051. That gets added and subtracted from our point estimate to get our interval, 0.375 to 0.477. And lastly, we always need to interpret our interval as the final step of the confidence interval. Dr. Godlewski's class can be 90% confident that the interval from 0.375 to 0.477 captures the true proportion of red beads in the container.